I don't really care. Let's say midnight.
Yeah.
But why wait? Like, then you have to like postpone your holiday celebrations.
Oh.
No, we're trying to perfect it for you. We'll make it like
Make it perfect? Okay.
We're gonna make it pretty for you.
Then I can celebrate.
Perfect.
Yeah, reason to celebrate.
All right. Okay, so let's have another reason to celebrate. Let's talk about food. Yay, team. All right. We're going to talk about simple harmonic motion because that's really what we're doing all this time, right? Now, early on in our conversations about simple harmonic motion, we defined it and we gave some examples of things that exhibit it. I would like for you, because it's been a little while since we've been together and having conversations, I would like for you to look back in your notes and find out what the definition of simple harmonic motion is. If something's actually exhibiting simple harmonic motion, what does that mean? And what kind of systems exhibit it that we have not talked about formally through notes? I'm going to give you a minute to look that up. All right. Michelle, did you guys figure out what simple harmonic motion was? And what did you have? What do you think it is?
A system in which the net force is proportional to the displacement from equilibrium and always directed towards equilibrium.
We okay with that? So we can put these two things together. F net is proportional to x. We just talked about this. If it's proportional, that means that it's equal to the displacement times what? Some sort of constant, right? So F net equals some sort of constant times x, and it's always toward the equilibrium. How can I incorporate that into this statement? I need a negative sign, right? Because I'm going to remember that this is a vector and this is a vector and they're going in opposite directions. So if something exhibits simple harmonic motion, we know that it must follow Hooke's law. Okay? That's great. Good for us. Now, in looking back through your notes, Peter, did you guys come up with any examples of things that exhibit simple harmonic motion that we haven't talked about? Maybe you've investigated last week, but we haven't like formally talked about? Pendulums, right? You looked at them last week, right? You watched them swing. It was really fun. But maybe we haven't talked about them super a lot. So when we were making a list of things that exhibit simple harmonic motion, we had the mass on the spring, and then we talked about other kinds of massy on springy things like bouncy, bouncy, bouncy. And then somebody threw this out there, and we kind of all blindly said, okay, right? Honestly, without really thinking about it. Because our teachers have been telling us since we were in preschool that a pendulum exhibits simple harmonic motion, right? Brittany's like, yeah, I totally remember my preschool teachers talking about that. This is simple harmonic motion, kids, right? I totally know. Circle time on the rug, and we're going to talk about simple harmonic motion. This is what happens when Ms. Carbling's in charge of preschool. Watch out. It would be great. So, if that's the case, if this is a simple harmonic oscillator, what does that mean about the net force acting on that bob? What does it have to look like? It has to look like negative kx, right? That's what we said. So we're going to find out if we're really true. If that kindergarten teacher was, in fact, telling you the truth. So there's the table. Here's my string. The mass on the end of the string. You would agree maybe that it's displaced from equilibrium at this point? All right. I would like you to draw right now a free body diagram. Oh, wait, that's been a long time. Oh, but it's good for you. A free body diagram of the mass. So all of the forces acting on the mass or the bob. I'm going to let you do that. Once you've got a picture, check with your neighbors. See if they agree. All right. Here we go. So, Casey Matthews, do you have any forces drawn on your bob? Force of the string. Where does the force of the string go? Back up. This way? And if I'm going to be a really good AP kid, I'm going to draw it directly from the object, right? We're talking being a really good kid, and we'll call that the force of the string on the bob. And I can put F sub t there if I want. Ft for? What does T stand for?
Oh my. Oh, tension.
Tension? Tension? Or I guess you could write F sub s for string if you wanted. That's fine. This looks really small. I'm going to make it bigger. Oh, now it's big. Okay, good. And Mr. Gunderson, do you have any other forces acting? What else you got?
I got force of the earth on the mass.
Where does that one go?
Pointing down.
Straight down?
Yeah. Force of gravity.
Anybody else have any other forces? Those are the two that I chose too. Good. All right. So far so good, yes?
Yeah.
All right. Now, again, we need to get it to look like this thing in order to convince ourselves that it's simple harmonic motion. So is there a net force acting on this object?
Yes.
Yeah.
Sure. Which way is it moving? Which way is it going to accelerate?
Towards the right.
Straight to the right?
At an angle.
And it, what's that?
At FG parallel.
Oh, what do you mean FG parallel? What does that mean?
Well, FG perpendicular goes straight down, like continues on from the string, and then FG parallel is like at a 90-degree angle to FG perpendicular.
Okay. So I completely agree. I just named them the other way.
Oh.
And it's fine either way as long as it makes sense to you. I'm just letting you know that because I was like, what? Yeah. So let me can I work on with that? Is that okay? So the way I'm understanding what you said, Michael, is that one goes like this. Is that what you're saying?
Where? Right there? Oh. Yeah.
Here. That's FG, and that's the one that you call perpendicular.
Yeah.
Okay. And it is totally personal preference. I called that parallel because I was talking about parallel to the string. Does that make sense? But either way works. So whatever makes you happy is good there. And then the other, excuse me. I know, right? What's happening? This part here is going to be the other one, parallel or perpendicular, right? How does this one here compare to this? How do these two forces compare?
Their magnitudes are equal.
Magnitudes are equal. What evidence do you have? Why do you think that's true?
It's not going to, the rope's not extending.
Yeah, it's not like accelerating up this way or down this way, right? Does that make sense? Sure, so that's okay. And so this thing here is the thing that's bringing this back towards what?
Center. Equilibrium.
Equilibrium, right? Yeah, and so that's actually kind of nice because that is, helping us to get towards, so I'm going to draw my equilibrium position in here, just to remind ourselves. So there it is, because it's going to go like, whoa, hello. Let's go back. There we go. Oh, there, okay. There we go. It's going to go down like that, right? So this part here is the part that's actually helping it go back to equilibrium. So I'm going to just kind of write this out a little bit just to make sure we're really okay. So F net, I'm going to call it parallel. The stuff that's going parallel to the string is Ft plus Fg parallel, and that's equal to 0. Does that make sense? F net perpendicular, and again, just to kind of clarify, that's perpendicular to the string, okay, is equal to Fg, but it's not all of Fg.
Perpendicular.
Fg perpendicular. I marked my theta here. Is that okay? And I marked my theta here. Are you okay with those drawings that just happened? Those thetas? And that they have to be equivalent? And so this part down here, that Fg perpendicular, I could write as Fg what?
Wait, the green one or the orange one?
Orange.
Orange one would be sine theta. That'll be a good sign.
Do you trust him?
You should, because I'm just going for that.
Yeah, see, he admits it. He talks before he thinks, right? So I want you to think first and then talk, friends. What do you think? Sine, cosine, tangent? Cosecant? Let's not do that one. Brittany, what do you think sine? Opposite hypotenuse, right? Okay. Yeah. So FG sine theta. Is that okay? I'm going to take it one step further. I'm going to write this as F net. So really the only net force is just Fg, which is mg. Is everybody okay with that, what I just wrote there? Mg sine theta. I'm going to make this a little bit smaller because I'm a little overwhelmed by the size of what's happening there. And now it's really little. Bigger. Having a hard time with my decisions here. That's my F net, right? We decided if something exhibits simple harmonic motion, then it needs to look like this. So now my question is, does this look like F net equals negative kx? Do these look the same?
Well, m's not a constant between different masses.
Right, but K's not a...
K, you're right, never mind. I quit.
No. Yeah, that does. Because the G sine theta is basically the same as the x. Like that's the displacement. Right.
G and m are constant. So G and m are opposite K.
Does anybody think it doesn't look the same?
Yeah, a little bit.
You're not allowed to talk anymore.
Okay.
There's no negative sign, otherwise.
There's no negative sign. Otherwise, yeah. A fourth grader would understand this, right? Two numbers multiplied together. Would a fourth grader understand this?
No.
No, they'd run crying because it says what?
Sine.
Like, what is that? Do these look the same? Brian's gut says, no. This one's a sine. If I graph this, like, let's think about it. If I graph this, what's it going to look like? Wiggly, wiggly, right? If I graph this, is it going to look wiggly, wiggly?
No.
Straight line.
No. Do these look the same?
No.
No. No. They don't look the same. So the short version moral of the story is what?
Addison lies.
I don't listen to Addison anymore. No, the short version of the story is that a pendulum, does it exhibit simple harmonic motion?
No.
No, it doesn't. This has to be true if it's going to be simple harmonic motion. This is what it is. Does this exhibit simple harmonic motion?
No.
No. Lies. Since preschool, I know that you all had that nerdy preschool teacher that made you are getting sleepy. Watch the simple harmonic motion, right? Like, I know this happened. I get it. But it's really not true. Not simple harmonic motion.
That's weird.
Right?
Yeah,
Lies, all of them. So then Michael says, because I can kind of read his mind, he's like, so what the heck are we doing then? Is that what you're thinking?
Yeah.
More or less?
It looks the same to me because like.
But that's a sign.
But K
If you
is
graph
just
that?
K is a constant and mg doesn't change, and x will change and theta will change, so sine of it will change.
But what,
Right, but if you graph it, it's going to right?
But what if you take not like what?
So go ahead,
What if
and then
you
we'll come back.
treat, like on your x-axis is sine theta instead of
Right, but does the third grader know what sine theta is?
no.
No. Like I can see you're convinced. Like I kind of feel like you're trying to convince yourself. I think because in your gut you're saying, but wait, I know that it's got to be something like this, right? It's got to be something like simple harmonic motion because Mrs. Green, my not art teacher Green, different. My kindergarten teacher was named Mrs. Green. That's why I'm saying this. She told me that it was simple harmonic motion. I know that it has to be. So let me reconcile a little bit. And then I think we'll feel maybe better. I don't know. This is generally where my super nerdo math students get mad at me, so I'm just going to warn you. Don't get mad. Don't get mad. Stay happy. The thing that's different between mg sine theta and the kx is the sine, right? Here's the thing. Well, actually, I want to think about what theta is first.
It's the negative sign too.
What's that?
Simon's a punk is the negative sign too.
Oh, I get it.
That was not good. What does theta mean?
You know it was good at.
What does it mean in terms of radians? What does an angle theta mean in terms of radians? You did this a long time ago. Do you remember? Theta is really just a ratio. Yeah, a ratio of what to what? Do you remember? What's that?
Like the distance on a circle of sine to cosine.
Yeah, absolutely. That's not the one I was thinking of, but that is totally true. Yes. You were reading my mind in a different way. That's great. Yes. I was thinking of the simpler version. At least the one that, like, when I learned this was the very first thing I learned about theta. Was that it's a relationship between this distance here, the part of the circumference. Does that sound familiar to you? The part of the circumference versus the radius of the circle? Did you guys learn this when you were doing this?
No.
No? The coolest thing about radians, let me show you just really quick because it's kind of fun. I just think, do you guys all love radians or not so much?
Love radius.
Okay.
If you don't love radians, let me show you why radians are cool. So if I draw two circles, and I'm going to attempt to draw two circles here. That's not a very good circle, but you can pretend.
I wouldn't say I love radians, but we've got a pretty nice friendship.
You got a relationship?
A friendship.
Oh, a friendship? Okay. Okay, so there are two concentric circles, kind of. You've got to pretend. Humor me a little bit. All right. If I draw some sort of angle out here, okay, the number of radians is the relationship between this length here and this length here. Okay, it's the ratio. So it's if I take my little tape measure and I go zoop, and then I go zoop, and then I do the same thing on this one, but I use this one and that one, those ratios are equal. Okay? When this distance equals that distance, that's 1 radian. And it's the same no matter which circle you use. That's the deal. That's what a radian is physically. What does it mean? Okay. It's cool. That's mathy though. Psh, who needs it? We need some physical description of what's going on. The arc length is like this distance here, right? It's the distance that the pendulum is going to travel. I'm going to call it x because it can travel some distance. Is that okay? And the radius is really the length of the string. So I'm really going to call theta x over r. And this then looks like even closer now. F net equals negative mg sine x over r. This is now even closer to this, but there's still a stupid little sign in here. Won't go away. Won't go away. I'm going to change that r to an L. I meant to do that and I forgot. Sorry. Haha, that's why we use erasers, right? This is the part that my math friends get mad at. Not really. Like, they just are in disbelief. There's this thing that we call small angle approximation. Here's my claim. You need to test it. Here's my claim. For small values of theta, the sine of theta is pretty darn close to the value of theta in radians. Okay? The smaller the angle gets, the closer these two are. We can show that mathematically. I'm not going to go through that right now. But I just want to test it out. So everybody needs to have a calculator. I don't want everybody to do this. Because I don't want you to just be convinced by your friends.
Thanks for listening.
Should we be in radian mode or degree mode?
So when you do the sine, I want you to be in degree mode, right? Because you're talking about 10 degrees.
Uh-huh.
So you want to know, I want you to find the sine of 10 degrees, and then I want you to find 10 degrees converted to radians. And then I want you to do the same thing for 60. Do y'all remember how to convert between degrees and radians? Anybody need a little fresher? It's okay if you say so. Okay, so if we think about it, the easiest way to do it that I know is how many degrees are right there? 180. And how many radians is that? Do you remember?
Power 2.
Pi. Right, that's pi. If you go half a circle.
Oh, I said power 2. I meant pi.
Oh, okay. Yeah.
Okay.
I thought you said pi over 2. I was like, ah.
Nope.
Yeah. So if you multiply 10 degrees times pi radians divided by 180 degrees, then that gives you the conversion. Does that make sense? All right. So I'm going to give you just a moment to find those 4 values. All right. Keegan, what'd you get for the sine of 10?
Sine of 10 is 0.17.
0.17. Uh-oh.
What did you do?
I don't know. There we go. And Jenny, what did you get when you converted 10 degrees into radians? She's like, I don't know. I'm still thinking. Oh, your calculator ate it?
No, I think. I don't know. Very being weird.
I'll come back to you. I'll go pick on Zoe. Is that okay, Zoe? Can I pick on you? What did you get for 10 converted to radians?
0.17.
0.17 what?
4, 5.
4, 5. What do you think about those two values? Are they kind of close?
Yeah.
I mean, you know, that's what, thousandths place? That's not bad. All right. And what'd you get for the sine of 60 degrees?
0.866025.
Something, yeah. And Esteban, what did you get for this one? 1.04. What do you think? A little bit different? A little bit close? Okay. So the game is that if you're talking about small values of theta, now every textbook says a little bit of a different thing. What does small mean? It's not like after you cross a certain threshold, then, oh my gosh, they're totally different. No. But generally, we're talking about things of about, I would say, 15 to 20 degrees. Above 20 degrees is kind of where people say, not so much, okay? But for small values of theta, instead of writing negative mg times the sine of x over L, we can say that f net equals negative mg times x over L. It's approximate, but it's pretty close for our purposes. And now, my friends, without much work at all, I think that you might be able to convince yourself, bless you, that that is the same shape as this one. What do you think?
Yeah.
Like, this takes very little convincing, I hope. Whereas the other one, the one that was hanging out with that sign, was kind of like, ugh, that makes me a little bit uncomfortable. Here we can say f net is equal to the negative. Now, Will, I need to exhibit full disclosure here because I feel a little bit bad. Because you were complaining about no negative, and so I just put a negative in. Did anybody notice that?
I did.
It was kind of sneaky, and nobody called me on it. Really? You guys just like, okay, Miss Carmeling, sure. Convince me that there should be a negative sign there.
Isn't it the same as gravity, and gravity is negative? Gravity's about it in the negative direction. Yeah.
Well, gravity's pulling down, but now we're talking about like this direction. So I don't know that I would use a negative like for the G. What does the negative represent here in this statement?
the displacements in the opposite direction as of the force?
The force and the displacement are opposite directions, right?
Oh, it's still like that.
Say it again.
It's still like that.
It's still like that, right? The displacement in our picture is to the left, and the force is to the right. Okay? So that's where the negative sign comes from.
So you can put the negative sign by the F instead of the F.
Sure.
Okay.
Yeah.
Well, yeah.
I mean, right? Because it's like multiplied by -1.
Yeah.
Yeah, you can put your negative wherever you want.
Thank you.
Certainly. Wherever you want. Just make sure you don't have too many of them, because that messes it up. Okay, so now is there anything else that I did that seemed a little unhappy before? Okay, just gotta call me on this stuff, friends. I think that stuff all looks constant. And then, my goodness, in fact, that kindergarten teacher was not lying. He or she was just saying, we're only talking about small angles. Probably thought that maybe the whole small angle approximation was a little bit beyond a 5-year-old. Maybe that was it. That's why. Okay. This thing here is like my constant. So for small angles, a pendulum does exhibit simple harmonic motion. For large angles, it does not. It's a more complex motion then. Now, we can take this another step further, because we can. We were together before and we were talking about the frequency, and that was 1 over 2 pi times the square root of k over m. Remember that? We derived it. We loved it. It was so cool. That was for a mass on a spring. I can do the same thing for this one. And in fact, you have a lab that's going to be written up by Friday that probably should include this information. F is equal to 1 over 2 pi times the square root of, so instead of writing k, because I like to make things ugly, right? You guys have learned this about me. Instead of writing k, I'm going to write this big, huge mess.
Of course.
Of course I would. Why wouldn't I? mg over L over m. But then Michael says it's not that bad. Why?
Because
That wasn't the right answer.
Because we just said mg over L is about k.
We do say mg over L is like our k. But you have mg over L over m.
All those m's are cancel out.
M's are going to cancel out. Yeah. So F is equal to 1 over 2 pi times the square root of g over L. Now, if you think back, way back, to your experience in accelerated physics, and not just experience in accelerated physics, the very first day that you had homework in accelerated physics, that was a long time ago. You did number 35 from chapter 1. I remember this. I know, right? Like, I have this ingrained in my memory. Probably not. But that problem, the reason I remember it is because every semester, these super crazy smart kids come in totally distressed because the question is so hard, it's so confusing, and oh my gosh. And the equation that it says is t is equal to 2 pi times the square root of L over g. And it says, show that that equation is dimensionally consistent. And this is just the reciprocal of this, right? It's like really no big deal.
Now.
And we just derived it. Like, how cool are we, right? That's pretty cool. Really quickly for me, humor me, show me that that is dimensionally consistent, would ya? Show me that the units work. I'd like you to do that.
You don't know me. You don't know what I got.
How are we doing? Are we okay? Does anybody need a little help? I can help you. I just need to know. We good?
Did she say math on a swing?
Swing.
Swing.
Mass.
Or is it mouse on a swing?
Mice have math.
That too, though.
I guess that would be a
So, what if for a pendulum lab we use like a 40-degree angle?
It's not going to affect it that much. Yeah, it's fine. Might be a. Yeah. All right. Are we ready? Are we okay? All right. I want to take a look at, not that, this, no, don't look at the answer.
What answer?
I know, right?
The end.
When I was in your position, I remember having a question like this and thinking it was the most ridiculous thing that I ever heard. Using a small pendulum of a length of 1.71 meters, a geophysicist counts 72 complete swings in a time of 60 seconds. What is the value of G in the location? I'm like, yeah, right. A geophysicist is going to take his little pendulum out and measure. No. Okay, so I remember having this conversation when I was an undergrad with one of my classmates and thinking it was the most ridiculous thing. 3 years after we graduated, he had gone on to get a PhD in geophysics, and he sent me an email. It's like, Sarah, you'll never believe what I just did. They were out in the field, right? And I'm not kidding. Pulls out the pendulum from his pocket to measure the acceleration due to gravity at the location. It's like, whoa! So anyway, this is not a totally made-up story. Like, this actually happens. I think it's hilarious. So anyway, now you can do the problem, okay? This is like real life right here for, real life and the life of a geophysicist.
Cool.
Think this through. You'll have to look at the units a little bit, but I think you can do it. Jenny Ty, what'd you get? Units are? How are we doing? Is that okay? The algebra there isn't super lovely, but it's not super hard. But is there anybody who'd like me to go through it again? I'm very happy to. Yeah.
I'm just getting confused between frequency and period.
Like which one to use, or?
Well, period is how long it takes to complete one cycle.
Correct.
Doesn't it take 1.2 seconds to finish one cycle?
That's what I got too.
No. Okay, so you have to look at the units very carefully, right? So you did 72 divided by 60, and that gives you 1.2. So if we have 1.2 what? We have to look at the units here. It's oops, let me write it correctly. 1.2 cycles per second. Does that make sense? So that can't be a period, because a period is a measure of time. And this is a number of counts, number of cycles per second.
So then 1 over that?
Would be the period, yes. Does that help a little bit?
Yeah.
The other way, if you want to think about it kind of more from a theoretical perspective, it's 72 cycles in 60 seconds. So that's going to be, it's got to be more than 1 every second. So that means that the period has to be less than 1. Do you know what I mean? Yeah. I mean, I don't know if that helps more than just looking at units, but yeah. Yeah, it's really, really important to remember that if you know period, you can find frequency. If you know frequency, you can find period, but they're not the same thing, right? They're inverses of one another. Okay. Were there any other questions that you had on this one before we move on? Okay. The last question that I wanted to go through today, I want to make sure that I didn't forget anything. Oh, I did want to show you this because it's kind of cool. So I don't know if you guys know Caleb Motes, but I made him make a video for me because he's my student helper. And so he swung a pendulum back and forth, and then I plotted it. I just wanted to double check and make sure that I wasn't, telling you crazy things. I told him to make sure his angle was small. And then I plotted the displacement versus time. That's quite nice, right? Mm-hmm. That looks like simple harmonic motion. And then I did some math, and you might want to be able to think about how you might do this too. That's why I want to make sure I show this to you. If I look at these numbers, I actually figured out this worked out really quite lovely. Okay, in terms of I looked at the B value, which is the one that's related to frequency. Okay, I worked backwards and I found the length of the string, and it was within 5% of what the actual one was. I was like,
Cool.
that's pretty sweet. Good for me.
Good job.
Yeah.
So what if on our lab we use 45 degrees?
So I wouldn't worry about it. It's not going to matter that much. Yeah. Is that fair? It's one of those, if I had not been gone all of last week, we would have done this prior, and then you would have, known to use small angles, but it's not appreciably different. Yeah.
Would we put that in our conclusion? We should use small angles?
you can. It doesn't matter enough as long as you kept it was that one of your, was that a control variable or a?
Control variable.
Yeah, then it shouldn't matter.
Okay.
Yeah. Because as long as you kept it constant, it should be the same.
Yeah.
All right, any other questions? I've got one more thing I want to look at with you. We probably won't have time to get through this whole question, but I will put it on the video so you can take a look at it, and I'll post this so you can see it. And I would recommend that you kind of know your way around this question, or one like it. We've got a graph here that shows the variation with displacement of the kinetic energy. So the x-axis is the displacement in centimeters, and the y-axis is the kinetic energy. It says in millijoules, just so that you know, okay? And it asks for you to find a bunch of things. All of these 5 things can be found from this one graph. So you've got a couple minutes. Why don't you get started with it, see how many of them you can get. Give it a shot. Just a minute.